Thanks for clicking in. This work is about human object interaction classification, and we propose a method called category query learning for this problem. Let me give you a quick preview first. The target of this work is to solve the challenging interaction classification in human object interaction detection. Previous methods all produce the classification scores by multiplying the interaction feature with the classification weight. They focus on improving the interaction feature, and our idea is to replace the static classification weights with adaptive category queries. These queries are learned through an additional image-level interaction classification task. By a lot of experiments, we find the proposed method achieves universal improvement over different methods, and it also obtains some interesting properties. The HOI detection task has two subtasks. As shown in the picture, the first is to detect each pair of human and object, like the person-horse pair in the image. This is similar to object detection. The second subtask is to classify each pair detected into some interaction categories, like the red category for the person-horse pair. HOI classification is very challenging. The reason is that, first, the semantics are abstract and even polysemic. Like the fly examples have different meanings in the first column of the examples. So the appearances are also diverse. The second reason is that when deciding an interaction category, you often need to take the relevant objects and backgrounds into account. For this problem, previous methods focus on improving the interaction feature. They use context modeling methods like GNN or attention module, or introducing other information like pose, masks, or visual language knowledge from models like CLIP. Some methods explore the representation of interaction in image, like human and object boxes in two-stage methods, union boxes or middle points in one-stage methods, or query in transformer-based methods. The queries in previous detection or HOI detection methods are instance-wise queries, which means each query extracts a feature mainly for one instance and will be matched to one instance. The query feature will be responsible for the classification on all categories, so they are not bound to a category. Some methods from other tasks, like multi-label image classification, use a different kind of query. The queries, we call category-specific queries, extract a feature from image for one category rather than one instance, and each of them will be responsible for the binary classification of one category, not all category. Our method uses such category queries, but we take an important step compared with previous methods. We replace the static classification weights with the learned category queries. So the queries are now some kind of weights that are adaptive to each image. Nothing else is changed, so the proposed method is theoretically orthogonal and complementary to previous methods. They focus on improving the feature. The design of our method does not rely on a specific baseline. We only need a baseline to provide two kinds of features. The first is image feature, and it can be taken from any feature extractor. The second is interaction feature, or we call instance feature. They are provided by any methods. With this abstract simple baseline, our method has two further steps. The first is to learn the queries. For this, we add an auxiliary image classification task. This task itself is not helpful. It initializes one queries for each category, like one query for ride, one query for hold, and it updates the queries through an image-level classification. The second step is to use the queries. For this, we multiply the category queries from the image classification task, like in the yellow region, with the instance feature from the baseline, like in the gray region, and get the instance classification scores in the red box. Our method achieves obvious improvement on three baselines. These baselines are representative of existing methods. The first QPIC is the first transformer-based method. It is end-to-end. The second is a method following the traditional two-stage pipeline. It is the SOTA of two-stage methods. And the third is a transformer-based method, and it is previously the SOTA. We can see that the proposed method achieves universal improvement on two benchmarks. It is also lightweight and does not harm the efficiency very much. And notably, it achieves the new SOTA on these two benchmarks. Here is an important ablation. Component 1 is the image classification task. It is another branch that we added. Component 2 is to replace the weight with the adaptive queries, and it is the key part of our method. We can see from the table that it is also the most important part to the final results. We also visualize the attention map to see what the category queries actually learn. We find that each query learns the semantics of its category. For the first example, in the same image, the hold query focuses on the baseball bat in the person's hand. The break query focuses on the part of the bat that is broken and in the air. And the second discovery is that each query is adaptive to different images. For the same query hold, the first image focuses on the baseball bat. The second image focuses on the upper body of the riders on the horses. This shows that the attention is adaptive to different images. So how is the performance improved? Our assumption is that the proposed category query is a global modeling of all instances from one category on the image, so it may be more helpful on images with more instances. We partition the images according to the number of instances for one category, from 1 to more than 5. We find that the proposed method, as shown in the solid lines, has a relative improvement on images with more instances from one category, and the previous methods in the dashed lines do not show such tendency. This proves that the proposed method is more effective on denser images. This is all for our introduction to this work. Thanks for your interest.